Yeah. The video cut out. I don't know why. Yeah, well, in the chart method, the next step is to react the strongest oxidizer with the strongest reducer. So we have how many oxidizers? We have 3 potential oxidizers. 1 is H plus alone. 2 is nitrate in combination with H plus. Sometimes people call this synergistic. In fact, we need both. 3 is water. And so all we do is we go to the chart here and then start up at fluorine. Fluorine is the strongest. And then just work our way down. So fluorine, the first one we'll hit is, see, none of these charts are perfect, unfortunately. And we start off with fluorine, and the first one we're going to hit is nitrate. Right here. Here's nitrate. So nitrate and H plus. That's going to be our strongest oxidizer. Okay, then our strongest reducer is going to be what? So we'll start off at lithium and then work our way up. So which one will we hit first? Copper. We'll hit copper.
For the nitrate and the hydrogen, they don't have to be like in one compound, do they? Can they just like both be?
Yeah, that's why it's written like this. It doesn't have to be in the same compound. So for example, you could get H plus from some other acid.
Yeah, so it could be like after the reaction when it's like H2 plus copper nitrate. Like it would still technically be an oxidizing agent because even if they're separate, or
Yeah.
okay.
Even if they're separate like this, but they have to be both be present. And so in that sense, they have to be combined. That is, they don't have to be combined into a single compound, but they both have to be present. And so when we react these, well, what's our oxidizer going to do? Our oxidizer is nitrate and H plus. So what we do is we'll just write that down. Nitrate plus 4H plus 3 electrons yields NO gas plus 2 H2O liquid. These are all aqueous here. So nitrate's aqueous and H plus is aqueous. The 3 electrons, we don't write any state for those. So that's what nitrate is. Nitrate's a reactant, and copper metal is a reactant. But over on the chart, copper metal is a product. And so when we look at this chart here, I come up to copper metal. There are 2 copper metals. Which one should I do?
Copper solid.
I should do copper solid, but there are 2 copper solids actually. Which copper solid should I do?
The neutral.
The bottom one.
The bottom one. I'm going to do the bottom one. Why?
2 plus.
Yeah, and also it's stronger. Remember the strongest one's next to or closest to lithium. And so the first one I'm going to hit is the strongest, which goes to copper 2 plus. But this is a problem because this shows copper 2 plus as the reactant here and copper metal as the product. So what I need to do is I need to flip that one around because what I have is I have copper metal as the reactant. So if I flip it around, that is just reverse it, I'm starting with copper metal solid, and then this is going to go to copper 2 plus 2 electrons. These are what we call half reactions. And what I do is I combine the 2 half reactions, but there's a trick to it. And the trick is that the electrons have to balance. So up here, the electrons are not balanced because I have 3 electrons on the left here. I have 2 electrons on the right. And so how can I balance those? The way I balance those is just by cross multiplying here. And the common factor is going to be 6. So what I'm going to do is I'm going to multiply the top one by 2. So there's 2 nitrates. 2 times 4 gives me 8 H plus. 2 times 3 will give me 6 electrons, plus 2 NOs, plus 4 H2Os. So that gives me 6 electrons here on the left. And then on the bottom one, I'm going to multiply by 3. So this is 3, 3, and then 3 times 2 is 6. The reason I need to do that is when we combine these, the electrons have to balance. That is, if I have 6 electrons consumed here, I have to have 6 electrons produced. And so I got to make sure the electrons cancel each other out. And so here, 6 electrons will cancel out the 6 electrons. And then I combine everything on the left and combine everything on the right. So everything on the left is going to be 2 nitrates plus 8H plus. That takes care of the top one. Then I'm going to combine it with the bottom one here, 3Cu solid. This is going to go to 2NO gas plus 4H2O liquid plus 3Cu2 plus. Okay, these are all aqueous here. So nitrate's aqueous, H plus is aqueous, and then copper 2 plus is aqueous. This is copper solid, that's NO gas plus 4H2O liquids. And then I'm going to look for driving force here. To look for driving force here, I'm going to compare their activities, basically. And so when I look at this, nitrate and H plus, that's our OA here. So nitrate and H plus is our OA. And so going forward, they take electrons over here. But if I go backwards, what happens? Well, NO and H2O going backwards loses electrons. And so that would be our reducing agent here. In other words, whenever we have an oxidizing agent on one side, the opposite side is going to be the reducer. And in this case, this is the reducing agent. The opposite side will be our conjugate oxidizing agent. This is the conjugate relationship here. And so nitrate and H plus, this is our oxidizing agent. Copper solid, this is our reducing agent. NO and H2O, this is our reducing agent. And copper 2 plus, this is our oxidizing agent here. Now, to figure out if this is going uphill or downhill, I'm going to compare. In the activity series, you compared the 2 reducing agents. It's nice if both reducing agents are elements, but they aren't. And so here we're going to have to use a chart, or we can compare the 2 oxidizing agents. Because of the conjugate relationship, we only have to do one or the other. But we'll do both, just to make sure we didn't make a mistake. So let's compare the 2 oxidizing agents. Which one's stronger? This is like a tug of war for electrons. Which one's stronger, nitrate and H plus or copper 2 plus? So we go to the chart here. We start off at fluorine, and then the first one we hit is nitrate and H plus. And then copper 2 plus is down here. So nitrate and H plus is stronger. So this is stronger. What does stronger mean? Stronger means higher energy, more reactive. Okay, this is weaker. Weaker means lower energy, less reactive, so it's downhill. If it's downhill, that means there's driving force. And the driving force is going from stronger, which is higher energy, more reactive, to weaker, which is lower energy, less reactive. So we only have to do one, either the reducing agents or the oxidizing agents, because the others will follow. But let's make sure that copper, it must follow that copper is stronger than NO. So lithium's down here, so we go up, and then we hit copper. We use this first copper, which is stronger than NO in water. And so that means this is stronger, this is weaker here. And so this is going downhill here. This is stronger to weaker, and we get driving force. So,
Will it always be like that? There's never a situation where it'll be strong and weak and then strong?
Never.
Okay.
So it's always going to be strong, strong, weak, weak, or weak, weak, strong, strong. If it's mixed, that is, if it goes strong, weak, then you did something wrong, because that would violate the conjugate relationship between the species. And so that would never happen. That's why you only have to do one, assuming you do it correctly. Yeah. So, signal replacement didn't predict reaction, but the chart method does predict reaction, and we're going to form a gas, NO gas, and we're going to form copper 2 ions. Copper 2 ions are blue-green high concentrations of blue. The NO gas, however, is colorless, and so there's one more reaction that took place there. NO gas is colorless, but what color was the gas?
It was tan and brown.
Yeah, kind of brown. And so what happens is the NO gets oxidized in air to form NO2. And the NO2 is a brown gas. Let's see. And to balance this, we'll need two NOs. And we'll form two NO2s. And so this just undergoes further what we call oxidation, the NO. Although this is not complete because nitrogen here is +4. Nitrogen can go all the way to +5. But +5 is not so easy to get. And so this is why we stopped here, +4. Okay, let's try another reaction. This next example, we're going to do, we're going to do sodium plus potassium iodide solution. Sodium plus potassium iodide solution. I want you to do it two ways. One, I want you to use single replacement, the A plus BX. And then two, use the chart method. If we use the chart method, this might not be the best chart here. But I'll leave this one up right now. All right, for single replacement, we usually use the activity series over here. This is in chapter 19 of our book. The activity series. Did you do that?
No.
Okay, do the activity series and see what you get.
Yeah, looks like it's uphill.
Looks like it's uphill, huh? Yeah, you're right. It is uphill. So, first off, what did you put for sodium, the formula? Na or Na plus? Na. Na is a solid, it's just a metal. All metals are solids, except for one. Do you know which one's not a solid?
Mercury.
Mercury. Mercury's the only liquid. Shoot, we got logged out of that. What's the formula for potassium iodide?
Ki.
Ki. Potassium iodide, you know people eat this stuff? Have you ever had iodized salt? Iodized salt is mostly sodium chloride with a little bit of potassium iodide or potassium chloride mixed in. Actually, not chloride. Iodized salt. Iodized salt has to have iodine. Do you know what the purpose of iodized salt is? People don't get enough iodine in their diet, or iodine, or iodide. You know, most people don't know chemistry, so they think iodine, iodide, all the same thing, right? So most people don't get enough iodide. Well, iodide's really important for your thyroid to make sure it's properly functioning. So it's an essential element, and because there's a deficiency of iodide, they usually supplement it in iodized salt. So let's take a look. Potassium iodide. You can buy it. Now foods, potassium iodide. Potassium plus iodine. I think potassium plus iodine is potassium iodide. But iodine and iodide, people are totally confused with it.
Professor,
Mm-hmm.
does that mean that we could actually extract that chemical from it and pull it out?
Iodine? Yeah. You could get it out. Elemental iodine. It's actually not that hard. But the people don't want it in the form of iodine because iodine, what's the formula for iodine? Iodine's formula is?
I2.
I2 is, you don't want to eat that. It doesn't taste very good, iodine. You know, because iodine's the stuff that I gargle with sometimes and do the nasal thing with. And it tastes like chlorine, basically. That's what it tastes like. I haven't done it in a while. You know, but I do that if I start getting a runny nose or if I start getting a stuffed nose. If I get a stuffed nose, then do a couple of blasts of iodine and it clears the nasal passages right out. It's not radioactive. I don't know why they have that symbol there. I don't know what this is. Potassium iodate. I don't want iodate. Potassium iodate is probably for purifying water, most likely. You know, killing the bacteria, viruses in water. It's camping, looks like. But anyway, during the Fukushima meltdown, you couldn't buy potassium iodide. You know, everybody ran out of it. They ran out of it because a lot of people were buying it. You know, just because. Do they say about potassium? If you want to see the NRC, what that is. NRC stands for the Nuclear Regulatory Commission. And they regulate all the nuclear reactors in the U.S. Nuclear Regulatory Commission, NRC, potassium iodide. Did I get that? This is what the government's saying about potassium iodide. Potassium iodide is a salt similar to table salt. Its chemical symbol, actually that's not a chemical symbol, that's a chemical formula. The symbol is just the symbol of the element itself. Its chemical formula is Ki. It is routinely added to table salt to make it iodized. Potassium iodide, if taken in time and at the appropriate dosage, blocks the thyroid gland's uptake of radioactive iodine and thus could reduce the risk of thyroid cancers and other diseases that might otherwise be caused by exposure to radioactive iodine. That could be dispersed in a severe nuclear accident or if there's a nuclear bomb as well, it would disperse. Not just radioactive iodine, but other radioactive isotopes as well. But since, you know, there's a lot of talk about nuclear bombs and this kind of stuff, you might think about this. You know, I know the government bought, what, $250 million worth of radiation drugs. The radiation drugs are different, though. This is totally different. That's for blood, you know, platelets. The radiation drugs that they have now stockpiled. But you know, potassium iodide would be just one line of potential defense against this. This reminds me of when I was a kid in elementary school. You know, I don't think they have these anymore, but when I was in elementary school, we had nuclear bomb drills, you know, if a nuclear missile comes. And you know what we did? We had this, we had these drills, and the thing is, okay, during the nuclear bomb drill, we would go underneath the desk. Yeah, like that's going to. Maybe, you know, maybe it'll help, depends on how far the point of impact is, but, you know. But now, you know, all this stuff is bringing back these memories of all that, you know. I was, you know, back then it was like, oh, you know, the Russians, they're so evil, and the Chinese are so evil, you know, they're going to destroy us with nuclear Armageddon. And now it seems like the rhetoric is getting back to kind of the same kind of thing as it once was during the Cold War. But anyway. So this is something you might think about. You know, right now it's not so hard to get. I think you can get this on Amazon. In case the unthinkable happens, you know, you might want to. It's cheap, $7.19.
Russia doesn't have the capability to aim their nukes specific targets.
Yeah, I'm not, you know, hopefully it doesn't get that far, hopefully, but, you know, if there is, let's say there is some nuclear blast, then you're just worried about the fallout.
The fallout.
Yeah.
That's not the only thing that falls out though.
What's that?
Iodine is not, radioactive iodine isn't even the only thing that falls
Yeah, no, it's not the only thing. Unfortunately, there's much worse things, but after Chernobyl, you know, the kids, this is most important for kids, I think. The kids in countries that the government supplied potassium iodide had much, much lower thyroid cancer rates than the countries that didn't. There's a big study in these European countries that did this versus didn't. And so in Japan, you know, they had potassium iodide, but they didn't distribute it to the population because they thought the population didn't need any supplemental iodide because they had plenty of iodide in the diet. But when you look at the cancer rates of thyroid cancer, there's definitely a spike in thyroid cancer rates in Japan amongst children. And so, well, they say they can remove the thyroid. If your thyroid becomes cancerous, they can remove it, but it's going to screw up a lot of things, you know, hormonally.
The thyroid atrophy anyway into the parathyroid, so.
Yeah, so maybe, but I don't know. I'd rather not lose it. I'd rather not lose it because how, you know, when people say, well, you know, it's like this thing. You think, okay, oh, these scientists, they know everything, but they still don't know all the proteins inside a cell. You know, that I told you that 10%, they're guessing, they're guesstimating that they don't know 10% of the proteins. That's the dark proteome in the cell. Yeah, and so, you know, you hear a lot of stuff that they know exactly what's going to happen, and do they really? I mean, how can you be so confident? So, anyway. Well, this is potassium iodide, but during Fukushima, when they ran out of potassium iodide in the US, you know, all these people were saying, oh, there's no more iodide, you can't buy it anywhere because everybody's buying potassium iodide in case there's fallout from Fukushima hitting the US, which there was. People were saying, well, use iodine, because when you consume iodine, it's going to take electrons from your tissue and make iodide, and so it'll oxidize your tissue. Yeah, that's why when you gargle with this stuff, it goes in. It's like purple when it goes in, but when you spit it out, it's clear because it's already oxidized. Iodide is colorless. Iodine is kind of purple.
I'd have fun just seeing that.
What's that?
I said I'd have fun just seeing it change.
Oh, yeah, watching the change in color? Yeah, then you know, for sure. I mean, if it's pretty dilute, you know, if it's concentrated.
Is that the medical disinfectant?
It's the medical disinfectant, right? It's also called betadine, I think. Betadine. And so when you go in to the hospital, we'll put it all over your wound. Betadine. Or povidone iodine. I don't know if betadine has other stuff in it, but there should be. This is an antiseptic. So there was an image on a wound there. I have this too for cuts and stuff. You know, this is in my little first aid kit when I go, you know, hiking or something like that. When I get a cut or a rash like that, I'll just put betadine on it. And so I have a small bottle of it. But iodine and iodide are two different things. Totally. Well, for a single replacement, what did you get?
Sodium iodide
Sodium iodide, good,
and potassium.
and potassium. Potassium is a metal, so it's solid. Potassium iodide, it's solution. So solution just means aqueous. So this is aqueous. Sodium and potassium salts are all soluble. Both of those are aqueous. Then what we do, this is single replacement, so we compare the two elements, A and B, and then see which one is more active. We want to go from more active to less active. And so we go back to the activity series and then take a look. Lithium's the most active over here. Lithium's the most active, and then well, here's potassium and here's sodium. So it looks like potassium is more active than sodium. So in other words, we're going uphill. You see potassium's higher in the activity series? That's uphill. So sodium's down here, potassium's higher in the activity series, so this is uphill, which means what?
No single place
No
reaction.
reaction. But we should try to be a little bit careful. We should say no
Single replacement.
replacement reaction. And so we don't predict any single replacement reaction. No single replacement reaction. Because we're going from less active, which is more stable, to more active, which is less stable. So sodium is less active, potassium is more active.
Do we need to memorize the activity
No.
series?
You don't need to memorize the activity series, it's given. But sometimes the activity series is missing things. This activity series is pretty good. It has gold, but some activity series, they don't put gold or platinum in there because students don't work with much gold or platinum. Silver, yeah. Copper, yeah. Though sometimes the activity series is missing gold. Like if you look at this activity series over here, lithium's the most active, and then rubidium. Well, that one's missing rubidium, and then potassium. But do we see, well, I see silver. Silver is here, but I don't see gold and platinum here. And so it's missing gold and platinum. But you know gold and platinum are even less active and more stable metals. You can kind of guess where it is. So this is correct. We wouldn't expect a single replacement reaction between these two. But, you know, to be safe, we should take a look at the chart method. And so why don't you try to figure out, did anybody finish the chart method on this? Yeah? All right. Well, let's take a look at the chart method now. So if we do the chart method, first we inventory. So what was the inventory? We have sodium metal, and then potassium ions, and iodide ions, and water. Now, there's a lot of mix-up between iodide and iodine. They're significantly different, and so we don't want to put iodine when we mean iodide. And the same thing with sodium. This is not the sodium you put on French fries. If you put this sodium on French fries and you ate it, you know what would happen? Yeah, potentially. They might be able to do like a tongue transplant on you.
Sounds like anyway,
go keep my things.
All right, then you label them. All right, so we got to label them. Okay, let's look at the assignments for these. Sodium, RA or OA?
Reducing
Potassium ions?
oxygen.
Iodide?
Reducing.
Water?
OARA.
Okay, so we have 3 RAs: sodium, metal, iodide, and water. Which one's the strongest? Sodium metal is the strongest. This is the easiest to take electrons from. Iodide would be the next easiest, and so this is how you reverse it. If you have iodide, you can easily form iodine. It's not that hard. All we need is an oxidizer that's strong enough to pluck an electron off iodide. You can get it. Water is pretty hard though to oxidize. It's really hard. But if you were able to oxidize water, do you know what you'd get? Oxygen gas. That's what you get. So by far out of these 3, sodium is going to be the easiest because you oxidize that, you form sodium ions. Sodium ions are pretty stable. We have 3 reducing agents. We only have 2 oxidizing agents: potassium ion versus water. Which one's stronger?
Potassium.
Well, take a look at this chart here. If we look at this chart, water's in the proper position here. Potassium ions are down here next to lithium. And so that means that water will be stronger than potassium ions. So here. Water is going to be the strongest oxidizing agent. And so the most likely reaction is going to be between sodium and water. Well, when we looked at the single replacement, was water even there? No, water wasn't even, it was there, but
We didn't account for
yeah, we didn't account for it. Because, why didn't we account for it? Because most of the time water doesn't react. Water is pretty stable. Water is pretty stable unless you react it with something very reactive. And that's something that's very reactive is sodium. Sodium is one of the top reducers here. It's number 2 on this chart. You know, it's number 3 on that chart there. Or no, actually it's, what is it on that chart over there? On that chart it's not, it's number 5. Yeah. It's number 5 on that chart, it's number 2 on this chart. So it's a powerful reducer. In fact, when we look at the activity series, we look at these. These are all very powerful reducers. Lithium's the most powerful, and then it's followed by potassium, and then barium, strontium, calcium, sodium. These are all extremely powerful reducers. These powerful reducers don't need much of an oxidizer to oxidize them. In fact, you could use something that's very stable, very reactive, like water. Liquid water is a strong enough oxidizer to oxidize these metals here, no problem. Normally we don't think of water as being a good oxidizer at all, therefore we always ignore it. Well, you can't ignore water if you're working with reducers that powerful. And so this is the reason single replacement failed here. Well, it failed in the sense that we might be misled that there's no reaction. There is actually reaction here. What is the reaction? And so we just copied off the chart here. And so let me go back to the other chart, which is kind of nice here. If we go back to the other chart, we have water as the reactant here. Okay, so water is going to be the oxidizer, and it takes 2 electrons. So 2 waters takes 2 electrons. 2 waters takes 2 electrons to form hydrogen gas plus 2 hydroxides. Okay, now sodium's the other reactant, but when I look over here, sodium's not a reactant, sodium's a product. So what I'll have to do is I'll have to flip it around so that sodium becomes a reactant. And so sodium's the other reactant. We go from sodium solid. This is going to produce sodium ion plus an electron here. Now, oftentimes they leave off the aqueous. You know, not here though, and so we'll put in the aqueous here. This is aqueous. This is aqueous. Okay, these are what we call half reactions, and then what we do is we combine the two half reactions to make the full reaction. But when we combine them, take a look at the electrons. Are the electrons balanced? No, how do I balance it? Double the top equation or the bottom equation?
Bottom.
I'm going to double the bottom equation here, and that's going to give me 2 electrons on the right side. Here. And what that means is that the 2 electrons here on the left side cancel out the 2 electrons on the right side. That's what we need to do in order to make this balanced. And so we're going to have 2 H2O liquids plus 2 sodium solids. This is going to produce H2 gas plus 2 hydroxide aqueous plus 2 sodium plus aqueous. Well, sodium and hydroxide is sodium hydroxide, it's NaOH, but we'll just leave it written like this. Okay, now we got to look if there's a driving force. So we're going to use the conjugate relationship to determine if there's a driving force present. So we called water the oxidizing agent? Yes, water is the oxidizing agent. So if water is the oxidizing agent, then the conjugate, you know, what's on the other side, will be the reducing agent. So that means hydrogen and hydroxide will be our reducing agent. Sodium metal is our reducing agent. That means its conjugate, sodium ion, will be our oxidizing agent. And this is how we're going to, this is kind of a tug of war, or you know, a hill, or whatever, however you want to visualize this. But this is our oxidizer, here's a reducer. Going backwards, hydrogen and hydroxide will be our reducer. And going backwards, sodium ion will be our oxidizer. And so we compare either the oxidizers or the reducers. It may be easier to compare the oxidizers. So let's take a look at the oxidizers here. Here we have sodium ion. Sodium ion is the second worst oxidizer. Lithium ion is the worst oxidizer. It's the conjugate relationship because lithium is a powerful reducer. It loses electrons easily, therefore lithium ion doesn't really have much of an attraction for an electron. So sodium ion, and then water is up here. So it looks like water is more powerful. It's closer to fluorine up there. So this is stronger. This is weaker. And so what that tells us is if we're going from stronger to weaker, that's downhill. And so this is going to be a downhill reaction. And we expect driving force to be present. We're going from a stronger oxidizer to a weaker oxidizer. Well, if that's the case, then the reducers must follow. Remember, it's got to be strong, strong, weak, weak, or weak, weak, strong, strong. And that means sodium must be a better reducer than hydrogen and hydroxide. And so sodium is number 2 on this chart, lithium is number 1, and hydrogen and hydroxide is up here, and number 5. And so this is stronger, that's weaker. And so this is an inverted hill, I think. And so we are going downhill, or in this way, going from sodium to hydrogen. And so this is a stronger reducing agent to a weaker reducing agent. And therefore, this is a potentially violent reaction, because what happens is the hydrogen gas gets generated. If that hydrogen gas ignites, then we'll have an explosion. And so if you were to mix sodium with this solution, you could have a potential explosion occur.
So even if there's no single replacement reaction, we still want to check the chart method to see.
So you have 2 choices. One is just skip the single replacement entirely and just do the chart. You know, because the chart method works for everything.
What conclusion would we come to, knowing that, like, if the driving force does this? Would we say that there is a reaction, or?
We expect reaction to occur. Over here, we do not expect reaction to occur because it's uphill. So it's like water. You know, water flows downhill. Do you expect water to flow uphill? This is water flowing uphill. We don't expect it. This is water flowing downhill. We expect it to happen. Okay, so one, you could just use the chart method. You don't bother with the single replacement. That's one. But the single replacement's a lot easier, isn't it? So two, you can memorize the exceptions. Do you want to memorize the exceptions? You probably don't want to memorize the exceptions individually, but you can memorize them as a pattern.
I feel like you could use a single replacement, and if it works, it works. If it doesn't, then do the chart.
Yeah, but how do you know? You know, you could go here. It could be, you're saying if it doesn't work, like there's no reaction?
If it does work, then like
Then, yeah.
you're done there.
Actually, that worked. That's okay too.
If it doesn't, then you check the chart,
You could check the chart.
because it would be faster that way.
Yeah, it could be faster that way. Or you could do this. These are I did 3 exceptions. 3 exceptions to single replacement, and those are the 3 exceptions to single replacement. Can you kind of summarize each exception? Take a look at each exception that we did, starting with chlorine. You know, why didn't chlorine, that one, fail? And then look at the next one we did, which was with copper and nitric acid. Why did that fail? And then finally this one. Why did this one fail? And those are going to be the 3 exceptions to single replacement. If you know why those failed, then you can be on the lookout that this is going to fail or potentially fail, and therefore I should use the chart method. Otherwise, single replacement should work. Uh-huh.
So in the reaction, the potassium iodide just doesn't do anything, it just remains in solution.
Yeah, it's what we call a spectator. The potassium iodide's still there, but nothing's happening. So it's like these electrons, but a little bit different. You know, so the potassium iodide's here on the left and it's here on the right, and nothing changed. Nothing happened to it, and so we cancel it out. This is what we call net ionic equation. Net ionic equation just looks at what's reacting and it ignores everything else that doesn't react.
So will it always be like that, where we only compare the strongest ones?
Yeah. So take a look at those and see if you can figure out. The species that gains electrons is called the, yeah. And so we'll assign the remaining roles.
So A would be the reducer.
Okay, so yeah, first we gotta see the roles. A is the reducer. A is gonna go from element to cation, so it's gotta lose electrons. And so we said B plus, the cation B is going to be the oxidizer. And then X is what role?
The anion?
Yeah. X, the anion, is going to be, well, did anything change with X?
No.
No. If nothing changes, we call it a spectator. And so it stays the same, it didn't change, it's just spectating, it's not really participating in the reaction. Really the main players here are A and B. Nothing happens to X. And so let's look at the exceptions. Single replacement works fine. It's nice, it's fairly straightforward pattern, but there's exceptions. The first exception is when what happened? The first exception is when chlorine plus potassium, what did we do? Chlorine plus potassium iodide? Yeah. Chlorine plus potassium iodide, and so A is chlorine, and A should be a reducer. Right off, that throws a flag up. Elements on the left side of the periodic table are reducers. Elements on the right side of the periodic table are oxidizers. So one, if I call chlorine the reducer, that's pushing it. Then two, do you see chlorine on the reducer side of the chart? No, in fact, chlorine is not a reducer. Chlorine is a very powerful oxidizer. So that's a red flag there. That tells me that, hey, this isn't going to work. In fact, this assigns what? So it's saying that chlorine is the reducer, and therefore what is the oxidizer
In that equation?
in this equation?
It would hence it would be, yeah, potassium.
Potassium plus is the oxidizer. And then I go, okay, is potassium ion a very good oxidizer? No. And so I'm thinking here, if I'm thinking chlorine's a reducer, this is all screwed up because chlorine is a much more powerful oxidizer than potassium ions. So this is wrong. Chlorine as an OA is much stronger than potassium ions as an OA. So yes, potassium ions are an oxidizer, but this is misassigned. Chlorine is going to be the strongest oxidizer here. And so it's going to oxidize something. Well, here, iodide should be a spectator, and there's also water. Which one do you think is going to be easier for chlorine to oxidize, iodide or water? Iodide. And so iodide is no longer a spectator. Iodide is going to be the strongest reducer present. And so the problem is, in this case, A turned out to be a stronger oxidizer than B plus, and therefore it failed. So whenever you're starting off with an element on the right side of the periodic table, that's going to mean that this single replacement format is going to fail. Okay, the next exception was the copper with nitric acid. Okay, there are more exceptions, you know, but the general pattern here is like this. I could have chlorine, I could have fluorine, bromine, iodine, something like that. Was copper and nitric acid. The roles that were assigned, copper is the reducer. There's no problem with that. That's fine. Copper is the reducer. The next one is that H plus is the oxidizer. And nitrate is the spectator. And so the problem comes here. When I look at nitrate, it's not on this one. Go back. When I look at nitrate versus H plus, who's stronger? Nitrate is stronger. And so in this case, nitrate is a better oxidizer than H plus. If nitrate's a better oxidizer than H plus, and you made this assignment, you know, what you're going to have to do is you're going to have to shrink yourself down to atom size, and then you have to prevent nitrate from reacting, you know? Otherwise, nitrate's going to attack. Do you think you can shrink yourself down to atomic size and prevent nitrate from reacting? Or maybe you can tell nitrate, do not react? Is that going to be effective? No, I mean, nature is going to take its course and nitrate's going to react. Nitrate's not going to care what you tell it to do. You could tell it, do not react. You're supposed to be spectating.
What if I do it really sternly?
But it's not going to work, is it? And so this is not a spectator. It turns out that nitrate is a stronger oxidizer than H plus. And so nitrate as an oxidizing agent is much more powerful than H plus as an oxidizing agent. And so this is misassigned. You know, both are oxidizers. And so nitrate has to be with H plus. It's a synergistic type of thing. And so this is the other fail. The other fail here, we can remember via this. Nitric acid has a name to it. When we look at nitric acid, it's a special acid. This special acid is called an oxidizing acid. All acids are oxidizing, because all acids want electrons. H plus wants electrons. But nitrate's special because the nitrate wants electrons more than the H plus. Versus HCl. You know, both of these are strong acids. Nitric acid and hydrochloric acid are strong acids. But HCl is not called an oxidizing acid. HCl is called a mineral acid. A mineral acid, well, H plus is an oxidizing agent. What about chloride? Chloride is not an oxidizing agent. Chloride is a reducing agent, and it's very weak. So chlorine's a strong oxidizer, therefore chloride's a very weak reducer. So you could eat chloride. Chloride doesn't have any taste. There's no problem eating this stuff. Whereas when we break down nitric acid, H plus, this is an oxidizer, but nitrate is a very strong oxidizer. In fact, nitrate is stronger than H plus. So this is why we call it an oxidizing acid. Oxidizing acid is not just H plus, but the anion. The anion is very reactive. Nitrate's not a spectator. So whenever you have an oxidizing acid, we have to be careful with that because the anion in an oxidizing acid is the oxidizer. So in this case, nitrate's the oxidizer. Let's look at this. HI versus HClO4. HI, do you know what the name of this is? Here.
Hydrogen iodide?
It's hydrogen iodide, but as the acid we call it hydroiodic acid. So when we look at hydroiodic acid, is that a mineral acid or is that an oxidizing acid?
Mineral.
It's a mineral acid. The only oxidizer here is H plus. Iodide is a reducing agent. It's a better reducing agent than chloride. When I look at this one, this is H plus and ClO4 minus. Do you know what we call this acid?
Commonly or just?
Yeah, the, well, systematic name. What's this anion, ClO4 minus, called?
Hyperchlorate.
Perchlorate is going to make what acid? Perchloric acid. Is perchloric acid an oxidizing acid or a mineral acid? Perchloric acid is an oxidizing acid. It's actually a very powerful oxidizing acid. And the reason is this. What makes nitrate a good oxidizer? Is it the oxygen or the nitrogen in nitrate that makes it a good oxidizer? Well, it's not the oxygen because the oxygen's happy at -2. It's the nitrogen. The nitrogen's unhappy because the nitrogen is actually going to be plus
+5.
+5. Right. +5 means it's electron poor. Even though it's got this net negative charge, that net negative charge belongs to oxygen, not nitrogen. So nitrogen is what we call electron poor, making this a good oxidizer. Nitrate's a good oxidizer. How about perchlorate? If oxygen's -2, what is chlorine in perchlorate?
No, I mean, 7?
+7. Well, what do you think about that?
That's intense.
That's a lot.
I mean, there's-
That's a lot.
so-
That means perchlorate is going to be a powerful oxidizer. In fact, you know, there are people talking about making, have you seen perchlorate before? Ammonium perchlorate is what they used to make at Pepcon. So there are people trying to make green rocket fuel. Have you heard that? Green rocket fuel.
Like just because it's green or environmental?
Environmental.
I feel like they just painted green everywhere.
they're looking for different oxidants. Oxidant may offer a boost to greener rockets, less polluting. Ammonium perchlorate is widely used as an oxidant in solid propellants that power rocket boosters and missiles, but it comes with serious environmental costs. There's a lot of perchlorate contamination in groundwater, like Riverside was dealing with this, so they have some things to clean out the perchlorate in the water, but also Nevada, you know, this was a big issue in Nevada. But they say that if there's perchlorate, you know, the perchlorate inhibits iodine uptake in your thyroid. Have you heard that? Perchlorate. Let's see. Concern about environmental perchlorate exposure centers on its inhibition of iodide uptake into the thyroid. Decreased iodine intake may decrease thyroid hormone production. Perchlorate exposure, therefore, might be particularly detrimental in iodine deficient individuals. So, you know, if you have perchlorates in water, you probably should supplement with iodide. You know, get the iodized salt, you know, that kind of stuff.
Is that something just like naturally occurring in Las Vegas that you're saying?
In Las Vegas, it didn't. It's from the plant. The plant had some runoff of perchlorate that got contaminated the groundwater, and so the water, the perchlorate in Nevada, it's gotten way better. It used to be high. I think it's much better now. Perchlorate was detected in the lower Colorado River in 1997. Perchlorate was traced upstream to the Las Vegas wash, which discharges into Lake Mead. The detection point were two perchlorate manufacturers. And so the two perchlorate manufacturers up here dumping perchlorate, unfortunately, into the desert. You know, a lot of people dump stuff into the desert thinking it's not going to do anything, but that turned into an environmental problem. And so since Nevada water had pretty high, Las Vegas water had pretty high levels of perchlorate, they tried to get rid of it. Oh, wait, is this? This is 2020. Chemical and Nevada drinking water won't be regulated despite this dark past. So I remember seeing this is a perchlorate remediation facility here. They had lowered it. There's a video that they lowered it, and the Las Vegas politicians were drinking water from not worrying about the perchlorate. And so the past 20 years of cleanup efforts have been a huge success. The concentration of perchlorates in Lake Mead have decreased from 15 parts per billion in 1997 to 0.4 parts per billion in 2020. That's huge. Pretty huge reduction. Go from 15 to 0.4. So they were making it good. 1 part per billion is equivalent to a drop of water in an Olympic-sized swimming pool. So sometimes, they send out these things from the water district. They test for perchlorate, so you can see how much perchlorate's in the tap water at your house. But anyway, perchlorate, there's other things, it could affect the iodine uptake or whatever. But this is a powerful, would you expect this to be a powerful oxidizer? Yeah, +7. And so this is an oxidizing acid, this is a mineral acid, because over here, iodide, is iodide going to take any electrons? No. It still might participate because iodide, is a pretty decent reducing agent, but, it's not going to be this. And so if you're dealing with an oxidizing acid, then it's likely that the single replacement method is going to fail. All right, the last exception that we looked at was what?
The sodium metal.
Yeah,
Yeah.
that was sodium metal plus potassium iodide, aqueous. And this one failed because, you know, we can label A, B, and X, but it ignored one other reactant. What was the other reactant it ignored?
Water.
Water. And in this particular case, we can't ignore water. How can you tell when you can and can't ignore water? It depends on how powerful the chemicals you are using are. And so, in other words, it depends on this. So we look at the conjugates. We can't ignore water as a reducing agent if we're dealing with oxidizing agents like these very powerful. So if I'm using like fluorine, gold, chlorine, I got to worry about water reacting. If I'm using oxidizing agents that are weaker, you know, then I don't normally worry about water. And so it's at the extremes. When we have chemicals at the extremes, what are the extremes? Well, if I'm dealing with lithium, potassium, rubidium, barium, strontium, I worry about water, because water fits right here. So if water is an oxidizing agent, I got to worry about these powerful reducing agents. So if water is an oxidizer, these powerful reducers will react. If water is a reducer, then these powerful oxidizers will react. And so when I'm at the extremes, I have to worry about water. If I'm not at the extreme, then I can ignore it most likely. And so let me give you some examples here of some reactions. So if I take iron and HCl, you know, is iron a pretty good reducing agent? Yeah, metals are pretty good reducing agents. Would you expect iron to be a good no. Iron's kind of on the left side of the chart, right? You see it?
Yeah.
It's not, you know, so far left. There are better metals, but it's here. It's literally in the metal area. So metals are reducers. Metals are pretty good reducers. So iron's a pretty good reducer. Then I look at HCl. Is HCl mineral acid or oxidizing acid?
Mineral acid.
Mineral acid. And what that means is that it's going to be H plus is the oxidizer, and chloride should be a spectator. And chloride is a pretty good spectator because it's fairly stable. It's not a very good reducer. The metals are much better. If you look at iron, iron's a much better reducer than chloride. Chloride's stable, we eat the stuff. And so in this case, the single replacement should work. And so I'm going to form iron chloride and hydrogen. Well, which iron chloride am I going to form?
The +3 oxidation.
Yeah. And so I should form the higher one. Iron forms 2 and 3, so I'm going to form iron 3 chloride, which is going to need 3 chlorides, and hydrogen gas. To balance this, I'll need 3 HCl's, and I'm going to form 3 halves of a hydrogen gas. And this is going to be aqueous, and this is aqueous. I can get rid of the fraction just by multiplying everything by 2. But before I do that, let's see if there's a driving force. So when we do single replacement, we look at the elements. This one, we might not even need the activation series, activity series. What would you rather have, you know? An ounce of iron in your pocket or an ounce of hydrogen in your pocket? Yeah, I'd probably rather have an ounce of iron than an ounce of hydrogen because hydrogen's potentially explosive. And so here, this is going from, is it? Well, I don't know. Let me make sure. I I have it right, because sometimes it's very tricky, because we don't know how things react in the powdered state. So I might have to take this back. So when we compare iron and hydrogen, let's take a look here. Here's iron, here's hydrogen, and when we look at this, what looks to be more reactive? Iron. Now that goes against intuition, because if I had a block of iron versus hydrogen gas, I would expect the hydrogen to be much more flammable than iron. But you have to compare in similar terms. In other words, if I had powdered iron, it might not be so similar. Iron dust testing, updated here on the 15th anniversary of the explosion. What was the explosion? I don't know what happened to the audio. Let's try this one more time. I don't know what happened to the audio. Maybe it doesn't look so spectacular. So it is flammable, iron metal.
What is a public safety power shutoff?
When fire threat levels are high, power may be shut off to reduce what.
And this is 14 minutes. This is a bit too long. 3 iron dust fires fatally injure 5 workers.
Everything was changed that morning. And
The 3 iron is the oxidation state?
No, 3 different fires.
the first thing the doctor told us, walking in the door, was he was burned 95% of his body, and we don't think he's gonna make it. There's nothing you can say to that.
January 31st, 2011. 2 maintenance workers were troubleshooting a problem with a bucket elevator at the Haganese Powdered Metals plant in Gallatin, Tennessee. Suddenly, fine particles of iron dust ignited when workers attempted to restart the elevator's motor. The CSB investigation into that accident was underway when just 2 months later, on March 29th, a similar flash fire burned another Haganese worker. At a news conference in Tennessee on May 11th, the CSB released laboratory test results demonstrating the combustibility of even small amounts of the iron dust when dispersed in air in the presence of an ignition source. Just 16 days after the CSB released those test results, on May 27th, a hydrogen explosion erupted in the plant. The blast shook loose iron dust accumulations from the upper reaches of the building, which ignited and rained down on workers.
Combustible dust is a serious workplace hazard across the country. Since the Chemical Safety Board was established in 1998, 3 of the deadliest accidents we have investigated have been combustible dust explosions. They are entirely preventable, just like the dust fires that occurred at Hagen's.
The Hagenese Corporation is a subsidiary of GKN, a multinational engineering company headquartered in the United Kingdom. The Hagenese Gallatin facility, located some 30 miles from Nashville, employs about 180 workers in the production of powdered metals with a capacity of 300,000 tons per year. The main product is over 99% pure iron powder, used primarily in the automotive industry. The manufacturing process releases combustible metal dust into the workplace.
The dust must be controlled and not allowed to accumulate. But when the CSB examined the Hagenese facility after each of the 3 accidents, we were alarmed to discover literally tons of accumulated dust on surfaces throughout the facility.
At the Hagenese facility, iron powder travels through the plant by a system of conveyors and bucket elevators. The belts on the bucket elevators had a tendency to become misaligned, causing the motors to overload and shut down. On January 31st, 2011, a maintenance mechanic and an electrician were sent to inspect a bucket elevator that had just malfunctioned to see if the belt was off track. It appeared to be aligned properly, and the mechanics radioed the control room operator to restart the motor. The dust collection bag house had been out of service periodically over the previous week. Fine particles of iron dust remained in the area of the motor. As the motor restarted, combustible iron dust was suddenly dispersed into the air. The 2 workers were immersed in a thick dust cloud. Almost immediately, the iron dust found an ignition source, likely an electrical arc from exposed wiring on the motor. A flash fire erupted, engulfing both workers. Both men were severely burned. The first worker died from his injuries just 2 days after the accident. The second survived for nearly 4 months, but died in May of 2011. After the first accident, the CSB documented that combustible iron dust was visible in the air and that it coated most surfaces up to 4 inches deep. These CSB investigation photos show the accumulated dust on elevated surfaces, where the dust could be readily dislodged and ignited. The CSB report noted that engineering controls, such as enclosing conveyors and installing properly designed dust collection equipment, are the best ways to prevent dust accumulations. But as this CSB investigation video shows, the plant's powder handling equipment was not adequately sealed. Combustible dust was always present in the air inside the plant. In this investigation video, dust particles ignite and sparkle as they contact an indoor hydrogen gas flare from one of the plant's furnaces. And employees told CSB investigators that dust collectors were often down for maintenance. Housekeeping measures were the last line of defense for removing the large amounts of dust that constantly accumulated on plant surfaces. But the CSB found that housekeeping at Hagenese was ineffective. Those conditions led to a second serious accident at the plant, less than 2 months after the first deadly flash fire. On March 29th...
Okay, so it's the same thing here. But these happen a lot. Whenever you have a fuel, especially in a powdered state, that's potentially explosive. So you have bakery explosions. Have you heard of those? Where there's a lot of flour accumulated in the ceiling. Flour is combustible. You have grain silo explosions. And grain silo explosions can be big. You've seen those. But you know, grain is very flammable. It's electron rich.
I think like Kansas and Iowa.
Yeah, right. And mostly in the Midwest, you have these huge explosions. Actually, is this one here?
I know a thing or two about tradition.
I know a thing or two about technology.
Always grocery shop on Sunday.
I'm gonna click that in. Yeah. Oh, this one looks already damaged. There she goes. Yeah. There it goes. Yeah. So even though this sounds seems counterintuitive, we just have to use the chart to tell us. There. And so we're comparing iron versus hydrogen. Which one's more active? Iron. It's surprising, but iron's more active. And so this is more active, which means it's higher in energy. And then hydrogen is less active. And so we're going from more active to less active. This will be downhill, and we expect a reaction to occur. And so in this case, we get a single replacement reaction. If we did the chart method, we get the same answer, basically. And so sometimes if we can keep track of, the common exceptions, so these are the 3 common exceptions, we can go ahead and continue to use the single replacement method. That works out nicely. All right, let's take a break, I guess. Yeah. Kept talking for a bit too long. Chapter 9 is just chemical reactions part 2. And so I'm going to introduce some of these topics, but we're pretty much going to take chapters 8 and 9 together. And so one thing I need to talk about are electrolytes, as well as strong and weak acids, and solubility rules. So let's take a look at electrolytes from chapter 9. There are 3 types of electrolytes that we have the strong electrolytes. Strong electrolytes are compounds that dissociate into ions when dissolved in water. So we just say strong electrolytes dissociate into ions. Into ions. So an example of this would be sodium chloride. Sodium chloride solid is white table salt, and you can take that table salt and dissolve it in water to form sodium chloride aqueous. But sodium chloride aqueous is what we call a strong electrolyte. And what's going to happen is it's going to break apart into sodium ions and chloride ions, aqueous. And so they dissociate into ions in solution. There's an animation here. Let's take a look at it. When we dissolve sodium chloride, it's called dissolution. Here's like a little animation of the dissolution process.
When an ionic substance, such as sodium chloride, is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules cluster about the anions with the hydrogens directed toward the negatively charged ions. On the other hand, water molecules interact with the positively charged cations through the lone pairs of electrons on the oxygens.
So this would be a salt crystal here, and the salt crystal is soluble in water. And when it dissolves, it splits up into ions. And these ions are independent of one another, so they're floating around independently like this. And so this is typically what happens when we have soluble salts. And so what are the strong electrolytes? The strong electrolytes are the soluble salts, the strong acids, and the strong bases. The strong acids, there are 7 common strong acids that we should try to memorize. The 7 common strong acids begin with HClO4. HClO4 is called HClO4 perchloric acid. HClO3 is chlorate, which makes chloric acid. HCl, which is called hydrochloric acid. HBr,
Hydroboric acid.
HI,
Hydroiodic acid.
yeah, good. And how many is that? 5?
Yeah.
HNO3,
Nitric acid.
nitric acid. It's 6, and one more. You know what else is a strong acid?
Sulfuric acid.
Sulfuric acid. Formula for sulfuric?
H2SO4.
H2SO4. That's it. Those are the 7 common strong acids. Now, if it isn't one of those, then we'll assume it's a weak acid, but, you know, that's a rule, that's not a law, so. In fact, you know what the strongest acid is? It's an antimonic acid. And they say that its strength is about 10 to the 19 times stronger than sulfuric. Can you imagine 10 to the 19 times stronger? It's unimaginable. That's it. So if you memorize the 7 common strong acids, then we can treat all other acids as weak, like acetic acid, weak. Phosphoric acid, weak. Oxalic acid, weak. The strong bases, these are the soluble hydroxides, etc. The bases are more complicated, and I don't want to get into it, so we'll probably just leave it like that. And so at the Chem 4 level, it's just the soluble hydroxide. 2, then we have something called the weak electrolytes. Oh, actually, let me do one more example. So another example of this would be HCl. HCl is normally a gas, so we'll call that hydrogen chloride gas. But when we dissolve it in water, then we'll call it hydrochloric acid, HClAQ. But HClAQ is a strong electrolyte, and strong electrolytes dissociate into ions. And so HCl should dissociate into what? Into what ions does it break up into?
H plus and Cl minus.
Yeah, H plus Cl minus, aqueous. We go on to the weak electrolytes next. The weak electrolytes partially dissociate into ions, so partially dissociate. Into ions. the weak electrolytes consist of the weak acids. So if it's not a strong acid, then it's going to partially dissociate. It's not going to fully dissociate. And so, let's give you the rest. Weak acids, weak bases, and some heavy metal salts. Metal. Heavy metals would be like lead. Is a heavy metal. Thallium, mercury. Those are all heavy metals. So if we compare a strong acid with a weak acid, let's take a weak acid like acetic acid. Acetic acid has the formula HC2H3O2. It's a liquid and it's soluble in water. When we dissolve pure acetic acid in water, we'll get HC2H3O2 aqueous. And this is a weak electrolyte. What a weak electrolyte means is that some of it will dissociate like this. And so I draw two arrows, a small arrow going forward and a large arrow going backwards. And it dissociates into H plus and acetate. So whereas a strong acid completely dissociates like this, a weak acid partially dissociates. And the amount of dissociation depends on how strong the weak acid is. Well, acetic acid is pretty weak. Since acetic acid is pretty weak, it's like, greater than 99% of the molecules of acetic acid don't dissociate, and less than 1%. Uh-huh.
Is that C2H3O?
Yeah, C2H3O2. And so if I had two beakers, one beaker labeled HCl, like this, aqueous, inside that beaker are just a whole bunch of H plus and Cl minuses. And so there's lots of free H plus. If I had a beaker that's labeled HC2H3O2, acetic acid, aqueous, then there's very little H plus. Most of the acetic acid will be as molecules of HC2H3O2. So let's say I had 99 HC2H3O2s, then one of those will be broken up into H plus and C2H3O2 minus ions. So in other words, it's mostly molecules of acetic acid and very few ions. So this is what makes acetic acid weak. It makes it weak because there's not much H plus. H plus is acid. And so the more H plus we have in there, the more acidic it is. So HCl is going to be much more acidic than acetic acid because there's so much more H plus present. Now these ratios are going to change. The stronger the weak acid is, the more it dissociates. The weaker the weak acid is, the less it dissociates. So there are even weaker acids than acetic acid where you barely find any free H plus in there. Weak bases are more complicated. Heavy metal salts we'll talk about later. Just partially dissociate. The last category we have are the non-electrolytes. The non-electrolytes are usually determined by if it's not strong and it's not weak, then it must be non. Non-electrolytes do not dissociate. Do not dissociate. So, example would be, well, everything else. And so what is everything else? Everything else might be like this. Do you recognize this? CH3, CH2OH? Know what that's called? Ethanol. Ethanol in pure form is a liquid, but you can dissolve it in water. And it makes ethanol AQ. But ethanol AQ does not dissociate into ions. It just stays as molecules. And so when we look at the ethanol molecules in a beaker, none of them are dissociated into ions. They're all CH3, CH2 OHs. So it's a non-electrolyte. So it doesn't go any further. Here's a precipitation reaction over here. We'll talk more about precipitation reactions here. This is a very flocculent precipitate, kind of low density. It doesn't just sink rapidly. This is some basic electricity here. Talk about. This is called a closed circuit. Closed circuit, the electrons can flow. The electrons flow from the negative here to the positive. So it's going to go through the light bulb, through this wire here, back to the positive. It generates a current which powers the light bulb. If the circuit's open, this is called an open circuit. You know, these electrodes, which are wires here, just the wires, don't touch. And so there's no way for the electrons to jump unless it arcs. You know, if the voltage is high enough, it could arc through the air. But this voltage is not high enough to make it arc. And so the light bulb doesn't go on. So here's a non-electrolyte, ethanol. Ethanol, none of it's dissociated. So here's ethanol, 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 and waters. And none of the ethanols have broken apart. So it's just ethanol dissolved in water. Versus the strong electrolytes, this copper 2 chloride is a soluble salt. And so that completely dissociates into copper 2 and chlorides. So you can see the copper 2s here and the chlorides in blue here. So that's completely dissociated. Over here we have a weak electrolyte. Weak electrolyte, we have molecules of acetic acid, and if we had about 100, or more than 100 of these, then only one of these is dissociated into ions, the acetate ion and the hydrogen ion. And so most of the acetic acid molecules are intact, that is not dissociated, and then once in a while we'll run across one that's been dissociated. You can easily measure the number of ions in solution by setting up a circuit like this. Ions conduct electricity, that is, they conduct a current. Yeah. So there are no ions here because nothing's dissociated in the ions. So there's no electricity. This would be an open circuit. Here we can close the circuit by having some ions here. The ions in solution can conduct electricity and light up the light bulb. Over here it doesn't light it up as bright because there's so few ions. You know, it's a weak electrolyte. Weak electrolytes are weak conductors of electricity, typically. Ethanol was in the news not so long ago. Let me talk about ethanol just for brief. Have you ever heard of deuterated ethanol? Some guy's gonna start a company selling deuterated ethanol. Do you know what deuterated ethanol is? Normal ethanol has a mix of hydrogens, isotopes. Do you know what the hydrogen isotopes are? There's H1 and then there's H2. H1 is just called hydrogen. H2 they give a name. What's H2 called? There's actually one more, H3. H2 is called deuterium. You know what H3 is called? Tritium. So deuterium is also given the symbol D. So this is why they call it D. Deuterated ethanol. I'm putting the D in drinking. Ethanol gets the blame for hangovers. So this medicinal chemist, Tony Zarnick, has started this company called, what's his company called? Company is called Deuteria, I think. Let's see what the company. First product is Sentia, packaged like whiskey. Oh, that's with GABA. That's different though. Hasn't done the deuterium. I think the company's called Deuteria. So, yeah, Deuteria Beverages. Deuteria Beverages has received patents on making ethanol D at tanker truck scale and using it to reduce the negative effects of alcohol consumption. So it's already patented. But basically, they're going to remove this hydrogen, which could be either H1 or H2, and then just only put H2 on there. And that would be deuterated ethanol. Why deuterated ethanol? Because it turns out in the metabolism of ethanol, you know, one of the first steps in the metabolism of ethanol is it's converted into something called acetaldehyde. And so when you take ethanol, it's oxidized in your body to acetaldehyde. Acetaldehyde is a class of compounds called aldehydes, and probably the most famous aldehyde is formaldehyde. And so it's like drinking formaldehyde. You want to drink formaldehyde? No, it's going to give you a headache. You might get sick from it. And so the whole idea behind deuterated alcohol, if you read this, is having deuterium here slows down the metabolism, you know, because it's a heavier hydrogen atom. And so it slows things down. It's called kinetics. And so if it slows things down, then you aren't going to get as big of a hit of acetaldehyde. And so maybe your body can process it, you know, if you metabolize the alcohol slower. And so that's the whole scheme here. We want to slow down the metabolism to produce less acetaldehyde. I mean, not less, but just distribute it over a longer period of time. But do you know the cost?
Yes.
The first screwdriver cost around $5,000. You can't pay $5,000 for a drink? It's hard to make deuterated alcohol. I mean, well, you could buy it. Like I bought D2O, you know, you could buy this stuff. It's not $5,000, D2O. That's deuterated water. D2O is not a lot cheaper. I don't know why this is so expensive. But anyway, the cost has definitely got to go down. So that's interesting. But even if you have deuterium here, it's not going to dissociate into ions. In fact, this doesn't really dissociate. But when it reacts in the body, then things get, you know, rearranged. The atoms get rearranged. And so, you know, it does make a difference what's on there, and how that interacts with other things. And the other thing that another article came up, it was kind of interesting. About green rocket fuels. You know, so people are trying to get away from perchlorates and make green rocket fuels. And so they're looking for different oxidizers like this, NABT, NE. An alternative to polluting ammonium perchlorate shows promise as a propellant ingredient. Ammonium perchlorate is widely used as an oxidant in the solid propellants that power rocket boosters and missiles, but it comes with serious environmental costs. And so, it's interesting. And in fact, this is interesting because it shows the scientific method, so I'll show that next time. You don't have it with me right now. But they're looking for green replacements for things like ammonium perchlorate and rocket propellants. Actually, this is it. This is kind of interesting. You know, in science, we should have open and free discussion. And so if there's somebody who disagrees, then, you know, they should be given a forum and so this is letters to the editor. So this is in response to an article on greener rockets. And so I thought this was pretty interesting here. Is this person. Having worked for the past 2 decades under the Office of Naval Research sponsorship on green replacements for ammonium perchlorate and rocket propellants, so this person's been working on it for 20 years. I was very pleased by Mark Peplow's recent highlight, an oxidant for greener rockets, in the Science Concentrate section of November 23rd, 2020 issue of CV News. Unfortunately, this highlight contains numerous inaccuracies and omissions. The highlight reports on the discovery of nitramino diacetic acid, bis 2,2,2 trinitroethyl ester, NABTNE, that molecule I just showed you earlier. This is called organic nomenclature. Fortunately, you don't have to do this yet, but if we go on to organic chemistry, then you have to start naming things like this. This is why people have a hard time in organic, because the nomenclature and the memorization's heavy initially, and then it eases off, but it doesn't become so bad. And this isn't so bad of a name at all, once you know the rules. By a group of researchers at the Ludwig Maximilian University, Munich, as a promising candidate for the green replacement of AP, which would be ammonium perchlorate. The Munich group used a 2-step synthesis with yields of 22% and 13% and 4.4 and 2.86%. For practical purposes, these low yields preclude its usefulness. So what he's saying here is that they made this greener alternative, but this greener alternative is not going to be practical. And so it's not really a good alternative. And then the authors responded. And so they got this debate going on here, which is great. You know, that's what you want to see. You want to see scientific debate, you know, with differing views. People arguing their different points of view.